Hello, I'm Bob Noakes, and on behalf of myself and John Stanley of the Information Factory, I'd like to invite you to our course, Introduction to Telecommunications. Along with your videotape, you received a textbook. The textbook is organized into the same 4 sections as this videotape. View a section of the videotape, then go back and read the same section in the textbook. At the end of the section in the textbook, you'll find a list of terminology that you should know and understand from that section. After the terminology, you'll find an examination you can go through to refresh your memory on the points covered. If you're having difficulty with a section, try going back through it, following along in the book as you watch the videotape. We'd like you now to sit back and enjoy our Information Factory course, Introduction to Telecommunications. Introduction to Telecommunications is the first of 3 courses presented by the Information Factory under the heading of Basic Telecommunications. The other courses available in this series are Voice Communications 1 and Data Communications 1. Welcome to Section 1 of our course, Introduction to Telecommunications. Now in Section 1, what we're going to do is we're going to introduce you to basic communications concepts and terminology. And we're going to do this through the use of telegraph circuits. Now, although telegraph circuits aren't much used nowadays, they were what all our present communication systems grew out of. So it makes it easier if we go back and look at these simple type of communication systems and use them to understand and build a structure of terminology and communications concepts. This is a telegraph key, and it's used to put the Morse code signals into the telegraph circuit. Now, in our drawings that we're going to look at and the terminology we're going to review, you will not see drawings of all the different components of the telegraph circuit like this. We're going to use different symbols to represent the parts of the circuit. Let's take a look at the symbols we'll use. The first thing we want to look at is the key or transmitter. Now the key, you just saw a telegraph key like this. We can also call the transmitter because it inputs information into the circuit. And we'll see it in our drawings as a symbol like this, showing the key and the contact closing. Next, we have the sounder or receiver, as we call it. The sounder or receiver is a device with an electromagnet and a clapper that's spring-loaded that usually makes a clicking sound corresponding to the key being depressed by the operator at the other end of the circuit. And we'll show the sounder or receiver as a symbol like this in our circuits with an electromagnet and the clapper and spring. Next is the transmission line or the link. You think of transmission lines or links as wires going across telephone poles, probably. All you'll see is just straight lines connecting the various points in our communication circuit. And finally, we have a battery here, or a power source for the circuit, and we show the battery or power source as a symbol like this in our network diagrams. In our basic communication circuits, what you're going to find out is all communications follows a model like this, where there's a source, or the sender, who communicates to the sink, which absorbs the message, or what we would call the receiver. Now the communications takes place over some sort of a link. Now the type of link between the 2 points determines the way the communications will act. For instance, is the message going to come over blind, or is the message going to come over and be acknowledged? Or will messages flow in both directions at the same time? All kinds of procedures. So let's assemble some basic communication circuits and take a look at the way information flows. This is the Simplex Circuit, where an operator at one end of the circuit can put messages in using the key, and they can be received at the other end of the circuit on the sounder. In the Simplex Circuit, because you only have a key at one end and a sounder at the other, messages can only move in one direction, from the originator or transmitter here to the receiver at this end. The Simplex circuit
has uses in modern communication. Even though it only allows transmission in one direction, which means you cannot send a message back letting the person know that you received their message, it can still be used for burglar alarms or signaling systems where you're turning something on or off at a remote point.
This is a half-duplex circuit. In this case, we have the one transmission line or link, and at each end we have a key and a sounder. Now an operator at this end, using the key, can send a message to the sounder or receiver at this end of the circuit, and the operator at this end can send a message back to this sounder. Because they share the one transmission line or link, only one operator can transmit at one time. This is because if both operators close their keys and send messages, the sounder will become confused. The Morse code symbols will begin to overlap. Now in this circuit, because it can transmit in both directions, we call it duplex. But because it can only transmit in one direction at a time, we call it half duplex. With the half duplex circuit, we now have the capability of sending messages in both directions. The advantage is we can now send a message back letting the person know that they sent their message and it was received correctly. This is called an acknowledgement to the message. In addition, we come up with a problem on half duplex. Since only one operator can send at any one time, the operators have to have some sort of training that tells them who can transmit in either direction at what time. This is called a line discipline. Now later on, when we look at what's called a multipoint circuit, we'll look at the line disciplines in depth. This is a full duplex circuit. In this case, an operator here can send a message to this sounder, and an operator here can send a message to this sounder. Since each of these links is across its own transmission path, what we have is the capability of being able to send messages in both directions at the same time. Now, in reality, to operate this circuit would take two people at each end, one copying messages and one sending messages. But with the full duplex circuit, we can send in both directions at the same time.
In most cases, you'll find out that the full duplex circuit is operated with a half duplex line discipline. That's because there's only one operator at each end, and he can only transmit or receive. Now this is important when we talk later in these courses about computer communications. You will find instances where you have a full duplex circuit and the circuit is operated in a half duplex line discipline or a half duplex manner. Now the full duplex circuit also has the disadvantage that it is more costly because you have two pairs of wires on each side, whereas in the half duplex circuit you only had one pair of wires. In modern communications that doesn't make much difference, but in the telegraph circuits where wire was one of the most costly items, the full duplex circuit was rarely seen because of the cost of putting it in. Cost was an issue in the construction of telegraph circuits, and because wire was expensive and laying the route out was expensive, there had to be ways of allowing multiple cities to share a telegraph circuit. Because if your city had very few messages, or as we say, traffic, for another point, there wasn't enough to justify the construction of your own private circuit. So what you would do is multiple cities would get together and construct a circuit that they would share, much the same as an old party line telephone system. Let's take a look at one of these circuits that we call the multipoint telegraph circuit. This is an example of a multipoint circuit that's being used to connect New York with 3 cities across the state. In this particular case, the New York circuit goes out to Buffalo, Niagara Falls, and St. Catharines. These remote points by themselves may not have enough messages to justify putting a circuit in to New York. So one circuit was built and they all shared it. The problem here is if any key is closed, all of the sounders or receivers will sound. Therefore, only one person can transmit at any one time. Now, the decision as to who can transmit is made by what's called the line discipline. And in the multipoint circuit, we'll have one of two types of line disciplines, either one called polling or one called contention. In the multipoint circuit, if all the keys were depressed at the same time, there would be confusion in the network. There had to be rules set down to determine who could transmit a message at what time and how you would know to receive a message that was sent to you. These rules were set down as what was called line disciplines. You trained your operators to know how to format a message and how to send it. We also call them protocols, which means here's the way you communicate. We're going to take a look at the first type of protocol, which is called polling. In the polling protocol, one of the stations, such as New York, is designated as the master, which means that station has control of the network. New York then sends messages in sequence, sends a message to Niagara Falls, do you have messages? Buffalo, St. Catharines, in effect sending a message, polling them to ask if they have data or traffic. If, say, Buffalo had traffic, when New York sent the message, do you have traffic, it would respond by sending back the message. New York would then send a short message back and say, I got your message and it was good, and it would return to polling the other stations. So everybody gets a turn in sending the messages, but they can only transmit when New York requests their message or tells them to transmit. Messages going from New York back out to the remote stations would happen in the opposite manner. New York would say, are you ready to receive a message? If Buffalo said yes, New York would send the message out. An alternative to polling is to have a contention protocol or line discipline. In this case, there is no master on the circuit. But if New York wanted to send a message to St. Catharines, the operator in New York would listen to the circuit. If no one was using it, the operator would send a small message called a bid to St. Catharines, asking if St. Catharines is ready to receive his message. St. Catharines would respond, ready to receive. At that point, Niagara Falls and Buffalo would know that St. Catharines and New York were using the circuit, and they would ignore any messages. New York would send its message, St. Catharines would let New York know it received it correctly, and then New York would send an end of transmission relinquishing control of the circuit. Once control is relinquished, any other station can bid for the circuit. This form of bidding to use the circuit is called contention. Protocols or line disciplines are very important in the operation of communication circuits. They are the things that allow you to use the circuit and send your information or message. Operators were trained to follow the protocols, and without them, the operation of the circuit would degenerate into what's called chaos. Nothing would get through. So please remember, we have the physical part of the circuit where the operator's opening and closing the key and sending dots and dashes to make the Morse code characters. But on top of that, those characters are formed into a line discipline or protocol to format the message and get it from one end of the circuit to the other. When Samuel Morse built his first telegraphs in the 1830s, they weren't the type of things you see in Western movies where the man's sitting down with the key, sending information, and copying what's coming back via the sounder. Instead, Morse's telegraph used a paper tape and a pen that the dots and dashes were transcribed onto automatically by the telegraph receiver. This type of receiving was the way the telegraph operated for many years. Let's take a quick look at the Morse telegraph. Rather than a sounder at the receiving end, there was a paper strip controlled by a clockwork mechanism. The paper strip moved continuously underneath a pen. Whenever the key was closed, current flowed through the circuit and a magnet drew the pen down so that it made a mark on the paper. Depending on how long the pen was down, the mark was either a dot or a dash. When the key was opened, current stopped flowing through the line, the pen moved up and a space was made on the paper. What we're going to see is this came to two different states within the circuit. When the key was closed, current was flowing, the pen was marking. The key was open, no current, the pen was spacing. We still refer to communication circuits in the state of either marking or spacing. This use of the term mark and space that we saw in the Morse Telegraph is handy because as we evolved into modern communication systems and started using computer communications, they're based on the binary numbering system, which means we only have the numbers 1 and 0, or on the front of the computer a light that may be on or off, or some other two-state type mechanism. So what's happened is now we come up to the modern communication systems and the word mark, or the line is marking, is equal to a binary 1. The word space, or the line is spacing, is equal to a binary 0. So we have a two-state communication circuit which builds up on into the modern communication circuits where we're sending ones and zeros. And marking and spacing can correspond to 1 and 0 in most of these modern systems. This concludes section 1 of our course. In this section, you should have learned a little bit about how we combine the various components to make a communication circuit. You also should have learned some of the terminology associated with those circuits. Now, some of this may seem a little basic and a little old-fashioned looking at telegraph circuits, but what you're going to find out is the terminology is important to proceeding on to the more advanced parts of the course. Now, if you've completed section 1, you might want to go back and read your book, and at the end of section 1 you'll find an examination and a list of terms to review and remember. Go through the terms, make sure you understand what they meant, and then take and go through the examination and check the answers. If you feel you haven't learned section 1, go back and review the videotape and follow along with your book. At the end of each section, we will review the terms you should be familiar with. The following are the terms to review for section 1. Bid, circuit, contention, downstream, full duplex, half duplex, key, line discipline, link, mark, master station, Morse code, Morse telegraph, multipoint, point-to-point, polling, protocol, receiver, sender, sync, slave station, source, sounder, space, telegraph, telegraph key, transmission link, transmitter, and tributary. Welcome to section 2 of our course, where we're going to look at telephone systems and telephone networks. The study of telephone systems and telephone networks is important to both the person that wants to work in the telephony field and the person that wants to work in the computer communications field. Understand, when you look at a modern communications network like this in a corporation, both voice and data are being combined, and the combined signals are being sent over standard telephony type networks, which are analog transmission, or digital networks, which are the type of computer communication networks. So whichever field you're going to go into, you must understand first the telephone systems. In the telegraph circuit, your hand actually moved the key or transmitter and put the information into the circuit. In a telephone system, we have a slightly different problem. How do we get your voice to activate the transmitter and put the information into the circuit? When you speak, your voice actually vibrates the air molecules in front of your face. These vibrations move in what we call waves through the air. When they reach the listener, it strikes the ear, and the membrane inside the ear converts that into electrical pulses for your brain. One of the things we must do is convert these air waves into the changes in the network, just like a telegraph key did, and then at the opposite end convert those changes back into airwaves which the person listening at the other phone can hear. We'll take a look now at a basic telephone such as Alexander Graham Bell built and how it performs all of these functions. In the basic phone, there's a box at one end that's filled with carbon granules. When the airwaves come in, they strike a metal plate here which moves in and out with the vibrations, causing the carbon granules to be squeezed together. This changes the amount of current flowing through the box. As the current changes, at the opposite end of the circuit, an electromagnet pulls on a thin steel plate. The plate moves in and out as the magnet's strength changes with the changes in current. This causes the steel plate to vibrate and put moving airwaves back out at the receiving end of the line. So the incoming vibrations cause the carbon granules to change the amount of current in the circuit, which changes the strength of the magnet, which causes the metal plate here to vibrate the same as the incoming vibrations at the transmitting end. The jump from a telephone that Bell designed to something like this, which is the crank-type telephone you see in old movies or maybe on an old farmhouse somewhere, was not that far. We still had the transmitter here, which is the section with the carbon granules. We had the receiver here, where you listen and has the metal plate that actually converts the electronic changes on the line back into vibrations for your ear. Looking at the phone, we can see, though, that the mouthpiece or transmitter, the earpiece or the receiver, will still be the same in a modern phone. In addition, we'll have this, which is called the switch hook. It's what you hang up the phone or you answer the phone with. And we'll talk about the switch hook controlling the line. When the phone is off hook, you're ready to talk on it. When it's on hook like this, it's disconnected from the line or ready to receive an incoming call. Taking a look at a modern phone now, let's see if all these same components exist. In this case, we have the telephone itself and the dial. Now the dial may be push buttons on the phone that you have at home. This is what you use to place a call to another part of the telephone network. Here is the cradle, which holds the handset of the telephone. In the cradle is a button which we call the switch hook, and this corresponds to the switch hook on the old crank phone we saw. When the handset here is placed in the cradle, we say the phone is on hook or disconnected from the network. When the handset is removed from the cradle like this, we say the telephone is off hook or connected to the line or the network. The handset itself is made up of the receiver, sometimes called the earpiece, and the transmitter, which is sometimes called the mouthpiece. The transmitter is where we speak into, and the receiver is where we listen. Telephones are connected into groups that we call networks, so that many phones within a network can communicate with one another. Through this network, various functions are provided. First, connecting the two calls together, and then the other is, when you actually talk, making sure that the two people can hear each other. In the balance of this section, we've divided the telephone into two different functions to make it easier to explain. And the two functions are called switching and transmission. Telephones are connected together through a system called a network. The network may be either the telephone system in your office or the worldwide telephone network that connects all dial telephones together. The concept of picking up your phone and dialing another number and being connected to another telephone somewhere is called switching. Switching is what allows these two telephones to be connected. Once the connection is established and you talk from your phone and are heard by the person at the receiving phone, this is called transmission, or getting the voice from this phone to the earpiece or receiver at this phone. Section 2 will be broken up first into describing the concepts of switching and then the the concepts of transmission. In present-day telephone systems, we think of switching as picking up the phone, dialing another number, and being connected to someone. In the early telephone systems, the connection was made through an operator. You picked up the phone, waited till the operator came on, then you gave the operator the number, and they made a manual connection between the points. We're going to go now to the Telephone Pioneers Museum in San Francisco and see how a manual connection was established through the telephone network.
Now this is an example of a cord switchboard which allows calls to be connected between telephones manually. This is a pretty modern version. Older versions had a lot more jacks and a lot more calls could be connected to them. This is the type of switchboard that was used in a business in the 1950s and 1960s as the console on a PBX or PABX. Now in this, cords are arranged in pairs so that electrically this pair of cords is connected to each other. When a call would come in from an outside line, one of these lights would light and flash. The operator would pick up, plug into the line, answer the call. The caller would ask for an extension number. Up here you see the extension numbers on the jacks. When the operator knew what extension it was for, she would plug the other end into that extension and the extension would start ringing.
In Kansas City, a man named Strowger was an undertaker. He decided that the manual method of switching telephone calls was not good because he thought that the operators were routing calls to his competitors and he was losing business. Strowger designed the first automatic switching system, which allowed the person who had the telephone to actually request the connection automatically without an operator doing the manual intervention. His early telephone system was based on the concept of stepper switches. Let's go now to the Telephone Pioneers Museum and look at how an automatic system based on stepper switches operates.
Now, remember looking at our basic telephone, the big problem is how do you connect this wire to another telephone somewhere else in the country? Well, you're going to see that now with a demonstration first of some step-by-step switching equipment, which is the earliest type of switching equipment used. This is what's called a stepper switch. Here are the electrical contacts which are actually going to connect the call. And what happens is the wipers here move up and down and rotate through the positions inside the stepper. Each of these electrical contacts inside could be connected to one telephone. There are 10 stages vertically on the stepper switch and 10 stages horizontally. So one switch could connect to 100 telephones. Now, if your telephone was connected to this stepping switch and you were going to call one of the other subscribers, as an example, say subscriber number 32, if you had a 2-digit telephone number, the first thing that would happen would be you would dial the 3 and the armature would step up 3 times. Then you would dial the 2 and the wiper would move 2 positions over. So 3 up and 2 over is position number 32, and subscriber number 32's telephone would ring. After the call was completed, the switch would restore to allow another call to be replaced. Now, looking again at the whole stepper switch here, all the switching function takes place down here. Up here, what you see is the mechanics that actually move those wiper arms and control the connecting of the call. There are relays here that make sure you're not really connected during the switching so you don't get all the noise back and eliminate certain electrical interference problems for you. Now, we said 100 telephones could be connected to this switch, but there's more than 100 telephones in the United States. So what we would do is this switch would connect you to 100 more stepper switches, which could then connect you to 10,000 telephones. Or those 100 stepper switches could connect to 100 more. And as you see, by going out through multiple stepper switches, you get more and more possible connections. So what you would see is if you have a 7-digit phone number, the first digit would move the wiper up here, the second digit would move the wiper around, then that would connect, and the next 2 digits would move the next stepper switch, and so on and so on. Now here at the Telephone Pioneers Museum, we have a sample step-by-step switching system which allows you to actually dial a call and watch it progress from here, which is called the line finder, which when you go off hook with your telephone, you get dial tone. There are only so many registers, as they call them, that can take a dialed call. So when you go off hook, the line finder finds your phone and feeds dial tone to it. Then as you dial, you'll see the call progress down digit by digit until a telephone rings at the other end of the dialed call. Now the first function you're going to see is when the telephone goes off hook, the line finder will seek it and give dial tone to the caller. Now we'll dial the telephone number 6 7 5 9 9 9 5, and the telephone at the other end should begin ringing. After the call is completed, all of the relays will restore and the switching equipment is available for another call. Now a couple of last words about step-by-step switching equipment. First thing is, as you noticed when the call was being dialed through, if you watch the tape carefully, this stepper switch was throwing numbers away. It started to step and it restored. That's because we were dialing 675, which was our own telephone exchange. So this stepper said, hey, I'm on 675 and so are the other phones being dialed, so we don't need to connect the first 3 digits, only the last. If it had been a toll call to another exchange, that would have been a different matter. Now something else. The line finder. When we went off hook, the line finder connected us to dial tone, like that. The problem here is, with a single line finder like this now, he's off hook, no one else can get dial tone. The stepper switch has restrictions in that once the stepper switch is in the process of doing something, no other calls can go through that stepper switch. So there's only one call at one time through a stepper like this. Whenever a telephone went off hook, the line finder connected to it and gave it dial tone. That telephone now effectively blocked anybody else from using this stepper switch. Also, as the digits were dialed through the levels of the system, each of the switches was locked up, completing the connected call. This meant that only one call could be placed through each of the stepper switches. To overcome the problem, telephone companies designed parallel stepper switches which allowed multiple calls to take place. Eventually, though, the volume of calls made the stepper switch an unwieldy device or design in telephone networks. To overcome the problems of the stepping switch system, telephone companies designed switching systems around what was called a common control. This was a computer device built around relay technology in the original switching systems. The common control allowed a telephone to go off hook and get a dial register. As the caller dialed the number, the digits went into the dial register. Now, unlike the stepper system where as you dialed the digits, the call progressed and blocked stepper switches, nothing happens in this switching system until you finish dialing the call. As soon as all the digits are in the register, the common control looks at the number, then goes down and sets up the connection through what's called a crossbar frame. Now, the way the crossbar frame is arranged, it can allow multiple calls to be set up in vertical rows through one frame, so that unlike the stepper switch where we have one call per switch, in the crossbar frame we can have multiple calls. Let's look at a crossbar system in action. Now in this particular case, there are rows of relays laid out in a matrix. When a call is placed through this type of a switching equipment, where the rows of relays meet in the matrix is where the connection's made. Now vertically, there are 5 relays in each vertical row. One connection can be made in each vertical row. Many connections can be made then across the crossbar switch at the same time, so that through one crossbar frame like this, multiple calls can be in progress. Now, the crossbar system also makes extensive use of what are called registers. When you pick up the phone, you get dial tone, you dial a number. Rather than stepping the number through as it's dialed like the step-by-step switch did, the crossbar switch saves the number until you're finished. Then when you complete it, it will dial the number out through the network. In this way, you're not tying up all the switching equipment if you half dial a number and hang up, or if you take too long to dial a number. Dialing registers are valuable within the network. They've got to serve multiple users. By time sharing the dialing registers, we're able to reduce the cost of telephone switching. Now, this is our sample crossbar switching system. What you're going to see is probably a little too fast to show really happen on videotape, but when the telephone goes off hook here, this originating register gives dial tone and says, hey, I'm ready to receive the number. And you can see there's a light on here indicating that. Now, we'll dial the number, and as we dial the number, it's being picked up by the register and held. Once the entire number is in the register, it switches through the crossbar system and the other phone starts ringing. With the common control switching systems like crossbar, it was easy to make the next transition in the industry, which was to take that mechanical computer out and replace it with an electronic computer, which provided more features and faster switching. Then the step beyond that was to actually take the crossbar frames out and replace those with electronic crosspoint switching. And in later courses, we'll talk about electronic switching. But understand, the important thing here is the transition from the stepper switch to the common control switch, in which an external box sets up and controls the calls, and also the crossbar frame, which is a matrix that allows multiple calls to take place through one switching mechanism. One final thing about the switching system. The telephone, such as in your office or business, is connected back to the telephone company via a single pair of wires. Over this pair of wires, all the functions of switching, signaling, and everything that needs to take place with the phone occur. This particular drawing, where we have a single telephone and a pair of wires going back to the central office, represents the telephone in your house or business, and we sometimes refer to this as plain old telephone service, a single telephone line, or POTS for short. In order to understand now how calls move through the telephone network, we're going to have to look at a telephone number and how it relates to the telephone network in the United States. Now, here's a phone number for the United States or for North America. The first part here, 3 digits, designate a geographical area, and that geographical area is somewhere in the United States, Canada, or the Caribbean islands. The next 3 digits here are what we call the central office or exchange number. What they mean is, this is the telephone exchange that the subscriber that you're calling is connected to. And in the old days, this designated a single building somewhere. Now, however, we can have physically multiple exchanges within one large building. And finally, the last 4 digits down here are the subscriber number or the person you're calling. So they would be subscriber number 4332 on telephone exchange 431. We're going to look now at how telephone exchanges are connected together. Now, there's a hierarchy of telephone switching in the United States. Various things with central offices like your home phone's connected to, and then there are toll switching systems and things like this that provide long-distance connections. The switching network in the United States has changed somewhat with what we call deregulation. We're not going to worry about that right now. We're just going to look at the standard models for how telephone switching occurs within the network and how calls are routed. Let's get some terminology down concerning telephone switching systems. First off, the central office is where your phone is connected to. We already told you about that one. Your phone, though, is connected by what we call a drop or a local loop, which indicates the actual wires going out to connect to a telephone. Between central offices are lines we call trunks. These are when a call goes from one central office to another, they go across a trunk, and there will be different kinds of trunks you'll learn about. There's inter-office trunks, inter-toll trunks, or toll trunks, which go into areas where you pay more money and things like this. But remember these terms, the drop or the local loop, and the trunk for calls between offices. This is a sample telephone network. In this particular case, we have 4 central offices that are connected together. And we have what's called a toll office. Now, in some cases, a central office like this would have telephones. You may have an office that all it does is connects long-distance calls across trunks. This is called a toll office. If I was going to make a telephone call from this number here, 751-4078, to 751-3892, the call would be connected through my own central office. If, however, I was going to call from 4078 to 598-9861 here, my central office would get the number, would then look up in a table the proper trunk, and connect across that trunk to the other central office and pass the last 4 digits dialed, which is 9861, and I would be connected to that subscriber, and the phone would start ringing. In some cases, if I'm making a call over a long distance, the call may be connected through a toll office, which would then seek out the shortest route and connect me to the other office, either 542 in this case or 598. Now, if all the trunks between my office and the toll office were busy, it's possible a call could be routed up these trunks and then down to the toll office, or over these trunks to another central office to the terminating central office. When the call is placed via the direct route, we call that the primary route. When the call is placed via an alternate route, we call that the secondary route. In this case, we're looking at the switching of a call across area code boundaries. Now here we have area code 415, which is in San Francisco, and area code 408, which is in San Jose. If I dialed a call from my phone 3458161 to 9462030, the call would be sent by my central office to a toll switching office, which would then seek out the toll switching office in the 408 area and pass the number to it. Then it would select the route, connect to the central office 946, pass the last 4 digits, and the phone would start ringing. In some cases, though, you have an area like San Francisco and San Jose, which has a high amount of traffic. What will happen is 861 in San Francisco, which is in a business district, and 946 in San Jose, which is also a business district, have a high volume of calls between them. The phone company may elect to put in direct trunk lines between those central offices, just because there's no sense in sending a lot of calls through the toll network if they are between 2 major central offices. So you may see this as a primary route and the toll offices as secondary. The decision on how to lay out the network is based on the amount of traffic between the central offices. In the past, the telephone network in the United States was connected much like the drawings we showed you. There were major and alternate routes between the COs, and a call placed from one part of the United States could go through almost any switching office to get to another part. However, that changed when the long-distance companies in the United States were deregulated. Competition was allowed with AT&T, who at one time was the only carrier. Now we have companies like MCI and Sprint providing long-distance telephone service. It was decided that these companies could provide service only over long-distance routes, that they could not provide service such as within an individual city or areas where there was a local operating phone company. When the long-distance carrier service was deregulated, the Federal Communications Commission and the Justice Department decided that the local phone companies needed to be protected. Because they were providing basic telephone service, they did not want that opened up to competition,
and have local phone companies forced out of business. What was done was a geographical area was designated that was called a LATA, or Local Access Transport Area. Within this area, only the local telephone companies can provide service. Therefore, if you call someone that's in the same LATA as you, that phone call can only be carried by the local phone company. If you call to another part of the United States and cross the LATA boundary, that call can be carried by a competitive carrier. When a telephone call is billed, the way the phone companies decide on the cost of the call is by the distance between the central offices. Now in this case, we're showing some central offices and mileage bands going out. Here is your telephone hooked to Central Office 346. If you place a call from your phone to this phone in 421, you'll be charged for a call in the 5 to 10 mile radius. If you place a call from your phone to this phone off of 946, even though the phone or the home it's in is in the 10 to 15 mile band range, the central office itself is in the 15 to 20 mile range, and you'll be charged for a 15 to 20 mile call. This is because the distance from the central office to a phone is unpredictable, but the location of the buildings where the central offices are is always the same, and these are recorded at the Federal Communications Commission in grid coordinates called V and H coordinates. The method of billing the call uses the V and H coordinates. Now in your textbook is an example of how the distance between two central offices is computed. Now the call will always be charged as if it went direct airline mileage between the 2 points. So if your call follows an alternate or secondary route, it will not be billed for the additional mileage. It will always be billed as a direct connection between the two terminating central offices. This concludes our subsection on switching. Remember, switching is the process of connecting the two telephones together. Now we're going to move into looking at transmission, or when the voice moves end to end, how do we know the voice is going to get there and be correct?